One of you say about introduction and theory behind atomic absorption spectroscopy, what we have seen in the last class.
Ma'am,
Yeah, Monisha, proceed.
atomic absorption spectroscopy is a technique in that free gaseous atom absorb electromagnetic radiation at specific wavelength to produce measurable signal. Signal
Okay.
means in that atomic spectrum. Atomic signal directly proportional to concentration of free atoms
Okay.
present in the optical path. Only alkali metals and alkali earth metals can be analyzed.
Okay.
Alan Walsh was the originator and developer in 1950s and 1960s. The theories, atomic theory began with John D. Dalton in 18th century. This concept was all atoms of an element are identical and that atoms of different elements can combine to form molecules. Niels Bohr atomic theory, quantum number, a partially charged nucleus, electrons orbiting around the nucleus. It became a Bohr model of an atom. Louis D. Broglie proposed quantized energy of electrons, which is including atomic absorption spectroscopy. Bohr can clearly elaborated on D. Broglie's theory, stating that no two electrons can share the same four quantum numbers. The theory of atomic absorption spectroscopy. Atoms have valence electrons, which is the outermost electrons of this atom. Atom can be excited when irradiated, which creates an absorption spectrum. When atom is excited, the valence electron moves up an energy level. Stationary
Yeah.
or restricted orbits can be determined by the emission lines. The resonant line is then defined as the specific radiation absorbed to reach the excited state. Resonance is two state in equilibrium. The Maxwell-Boltzmann equation gives number of electrons in any given orbital. It relates the distribution to the thermal temperature of the system. Planck proposed radiation emitted at equals to h mu, which is related to Einstein's equation equals to mc square. The energy of the system can be used to predict the frequency of radiation. Mu is equals to c by lambda because only certain wavelengths are allowed and each atom has a unique spectrum. Both atomic emission and atomic absorption spectroscopy are used to analyze samples. Atomic emission spectroscopy measures the intensity of light emitted by the excited atoms. Atomic absorption spectroscopy measures light absorbed by atomic absorption. Light is typically in the visible or ultraviolet region of electromagnetic spectrum.
Okay. Thank you, Monisha. So you have given information on all the points what we have discussed in the last class, and very good. We'll move on to the next title in atomic absorption spectroscopy. So hope you have all have learned introduction and theory behind atomic absorption spectroscopy, how absorption takes place at atomic level in a molecule. Okay, now let's see how the molecule is converted to atom in order to analyze by atomic absorption spectroscopic technique. Okay, so let's move on to the third part, that is types of electrodes. According to your syllabus, we have covered two parts, introduction and theory. Okay, introduction and theory has been covered, and remaining portions are types of electrodes, instrumentation and applications. Now let's see about types of electrodes. Whether you are getting my voice clearly.
Yes,
Yes,
ma'am.
ma'am.
Okay, then let's proceed. So what are the types of electrodes? Here electrodes represents through electrodes only we are going to get light radiation source. That means radiation for analyzing the atomic absorption. For absorption purpose, electromagnetic radiation is passed from an electrode. So electrodes are nothing but source of light in atomic absorption spectroscopy. And they are unique in atomic absorption spectroscopy when compared to other spectroscopic methods. That's why we need to discuss this title separately. Along with instrumentation, it should be discussed, but it is given separately since it is unique in atomic absorption spectroscopic technique. Okay, so types of electrodes. Electrodes are nothing but here source of light. Source of light for analyzing the atoms. So what are the types of electrodes we use? Let's see. There are two types of electrodes. One is HCl lamp, that is hollow cathode lamp, and another one is electrodeless discharge lamps, EDL. HCl and EDL. And these two are types of electrodes. Among these two, hollow cathode lamp is widely used. Which one is widely used? Hollow cathode lamp, not EDL. Okay. So what the cathode, the name itself, it indicates that an electrode, right? Cathode. You can observe the image. It has a cathode inside it, and it will be having just a minute. So electrodes will be present inside the source and in the hollow tube. You can find the tube which is made with like a hollow shape, so that it is called hollow cathode. Since at cathode only the atom is going to emit the radiation, so that it is particularly mentioned with cathode. So whichever radiation you want, if why we are particularly mentioning cathode in hollow cathode lamp means this cathode will be made with or coated with the element what you are going to analyze. That means what atom you are going to analyze from your sample. For example, if you are analyzing sodium metal, the cathode will be coated with sodium metal. Okay, so that it will emit the characteristic radiation of sodium that is required to absorb by the sample. So sample also will be having sodium, and the particular source of light also, that cathode also must be coated with that particular metal ion. Okay, so that is why cathode is specifically mentioned in the name itself, source of light itself. So cathode is present in a cylindrical tube, so that is called hollow cathode lamp. When it is electrically heated, when the electrical current is given in between the electrodes, that is cathode and anode, what actual process will occur in this hollow cathode lamp means what source of light we have seen for UV and visible. So that if you recollect that point, it will be easy to understand about hollow cathode lamp. What is the source of light for UV and visible we have discussed? Can anyone say the source of light for UV and visible? Only Monisha is active in the class. What about others? So nobody is listening. If you're not able to give answers orally, you can give it in the chat box also, it said, right? So what is the source of light for UV and visible? Yeah, Monisha, you only say, ma.
Deuterium and tungsten.
Yeah, deuterium and tungsten lamp. So that is also lamp, and it is coated with hydrogen, right? A deuterium lamp is nothing but hydrogen, isotope of hydrogen, where tungsten is coated with tungsten element. So when it is electrically heated, it was emitting UV and visible radiation required for sample analysis. The same concept only applied here, where hollow cathode lamp also has the cathode and anode anode electrodes, and this cathode will be coated with a particular element what we are going to analyze. It is not the common element which is coated with the coated over the cathode. It is the specific element what you are going to analyze from your sample. In case if you analyze potassium, it must be coated with potassium. If it is you are analyzing calcium, then it must be coated with calcium. So specific for each and every sample, you need to purchase different hollow cathode lamps. Okay. So that means cathode must be coated with the analyte of interest what you are going to analyze by atomic absorption spectroscopy. And now what actual process will occur to get the radiation means, that is visible radiation, UV visible radiation. And see the first processes, and this cylinder will be filled with inert gas. Okay, why the cylindrical tube is used means it is filled with inert gas. Okay, so in that inert gas it is dipped. Where what all dipped? Electrodes, cathode and anode. Now the process sputtering, the first process sputtering occurs. That means when the electrical current is given to the electrode, what happens? And the organ gas, inert gas present in it will get activated. That means it will go from neutral state to excited state, ground state to organ gas. For example, organ gas, it will be going from ground state to excited state. That means it will get ionized. Argon atom, that is neutral gas, it is in gaseous state, right? Inert gas in gaseous state. So when the electrical current is passed, it will get ionized, and the ions, positive ions, will be moving towards cathode, and it will make the metal coated over the cathode. It will be moving towards cathode. It will, what it will do, it will collide with the metal ion coated with the coated over the cathode. And what this metal ion will do, it will get excited and goes to excited state, from ground state to excited state. Whatever metal present, if sodium metal is present, it will be going from ground state to excited state by means of colliding with the inert gas. Okay. When electrical energy is given, that is electrical current is given, organ gas, that is the inert gas filled inside the hollow cathode lamp, it will be getting ionized, and it will be moving on to cathode, and it will be colliding with the, or interacting with the metal present in the cathode, whereby it will absorb the energy, and it will be moving to electrical energy. It absorbs electrical energy and goes to the excited state. What absorbs electrical energy? Cathode, that what means metal present in the cathode will absorb electrical energy. From where it absorbs electrical energy? By means of colliding with the ions present in inert gas. What ions are present? What is the example for inert gas? Argon, neon, this all. Now here you can see argon gas. Okay, so they will strike when it is striking at the cathode. Whatever element present in the cathode will go to excited state, and in excited state is what? Unstable state. And to come to ground state, the sodium metal will emit the characteristic radiation. It will emit radiation energy. It has absorbed electrical energy. After going to excited state, it will be emitting the radiation energy. So that radiation, whatever emitted from the metal, will be of characteristic radiation for that particular metal. Okay, that characteristic radiation is used for analyzing sample. And that will be passed to the monochromator, and monochromator will convert it into monochromatic light. It will avoid all unwanted radiation, and it will be passed to the flame. So this is how hollow cathode lamp functions. So what are two important parts it has? Means chemicals it has. Inert gas, one is inert gas, another one is cathode. A cathode will be coated with, specific cathode will be coated with the particular element what we are going to analyze in the sample. So for each and every element, we need to get another new electrode, new source of light, new HCl. HCl here represents hollow cathode lamp. Okay. And you can find the schematic representation of hollow cathode lamp here, and this is how in the second picture you can observe how hollow cathode lamp appears. Inside the tube you can find the hollow and means cathode, and it is a cylindrical tube. It will be filled with inert gas. Okay, and you can find the mica disk for isolation, then standard or coded versions in order to alignment pins for alignment of waves, for that then larger gas volume for long lifetime. So that only it is filled in a cylinder. Okay, that's what it is called as hollow cathode lamp. Then special cathode technology for clear signals, then high quality window material. So this all about HCl lamp, how it is appearing in the instrument, or how we will be using in the instrument. So now what source actually does, it absorbs electrical energy and it converts it to radiation energy. That is the actual mechanism of hollow cathode lamp. It takes electrical energy, it absorbs, and where absorption takes place in the source at the atom present in the cathode. When it is going to excited state, it will emit the radiation energy. So to move from ground state to excited state, it absorbs electrical energy, and to get relaxed from means excited state to ground state, it emits the radiation energy. That radiation is the source of light in atomic absorption spectroscopy. This is next lamp, that is electrode less discharge lamp. No electrode is having here, only lamp and RF coils. Instead of electrodes, radio frequency coils are used in electrode less discharge lamps. And you can find here quartz window, and it will avoid the absorption of UV radiation comes, right? That's why quartz window is used, since quartz is transparent to UV radiation. Okay, it will not be absorbing UV radiation. That's why quartz window is used instead of glass window. And then even hollow cathode lamp also made with quartz window only, for where the radiation is passed to the sample. The EDL houses a sealed quartz tube containing argon gas. Inside this also argon gas and a metal of interest is filled. Okay, so inside the tube we are not coating over the cathode like a cathode lamp. It is electrode less lamp, but inside the tube it has both argon gas and metal of the interest. Okay, whatever sample metal I told, sodium, if you are analyzing, then sodium metal it should be filled with. Then the quartz tube is under high vacuum. A radio frequency, you can see the radio frequency coil. So radio frequency or microwave coil surrounds the lamp. You can find the radio frequency coil surrounding the lamp, and it is approximately 10 times more intense than a hollow cathode lamp. So it will be higher intense than hollow cathode lamp, and unstable output of radiation occurs. Then only available for about 15 elements. It is available for only 15 elements, not for all the elements. Okay, but it is more intense than hollow cathode lamp. But we will not be using electrodeless discharge lamp widely in instruments. You could find HCl lamps widely in the instrument, but there are options of two types of electrodes are used for source of light in atomic absorption spectroscopy. One is HCl, another one is EDL. HCl is hollow cathode lamp, EDL is electrodeless discharge lamps. And now we'll move on to the instrumentation part. So what generally a spectrophotometer will have, what are the common parts of spectrophotometer? We require electromagnetic radiation source. For that light source we need to select. That's what we have seen now, the electrodes, which will be giving source of light, which will be giving radiation. After getting radiation from source, what we have to do, we have to convert that light to monochromatic light. So from source whatever light is coming will be polychromatic light, so that will be converted to monochromatic light by means of monochromators. And then after monochromators, what will be using, sample compartment will be there, sample analysis. Then after absorption or emission, it will be going to the detector for detection purpose. Then recorder will read out the signal. So this is the common part of any spectrophotometer. Here also we'll be finding, but according to the principle of analysis, it will be varying. Can find the first part as hollow cathode lamp, cathode and anode, and the light radiation is coming from cathode, and it is going to the chopper where it is passing the unique radiations and to the flame. Here flame is most important. Let me will discuss briefly about a flame or atomizer, where atomizer name itself you can understand that the solution from neutral molecule, it is getting atomized in the flame energy, thermal energy. Okay. So what are the energies involved in atomic absorption means, here we are applying electrical energy and radiation energy is coming from the source, and it is passed to the thermal energy, into the flame, which contains high thermal energy, and where the atom is formed, and atom will absorb that radiation energy at means from ground state to move from ground state to excited state, it will absorb the energy, and then it will be going to the absorbed remaining energy will be going to the monochromator. Here monochromator we are keeping behind the flame or behind the sample compartment. Okay, not before the or not immediately after the hollow cathode lamp, since from the flame you will get many polychromatic lights. In order to select only monochromatic light that is coming from the selected metal, we need to use monochromator after the flame source. And then a lens to focus the monochromatic light to detector, and detector will be of same detectors whatever we have seen under UV visible spectrophotometer: photovoltaic cells, phototubes, photomultiplier tubes, photodiode arrays, photon diode arrays. These all will be the detectors in flame photometric analysis also. Okay, so we need to discuss, we already have seen what is hollow cathode lamp. Now let's see what is flame atomizer and how the sample is converted in flame into atom dissolve. Okay, monochromators, all prisms are grating monochromators. Monochromators detectors will be common, what we have used and what we have seen under UV visible spectrophotometer. The difference you could find here as sample compartment and the sample source of sample and source of light. This only will be varying in atomic absorption spectroscopy. Now let's see about briefly about each part and this content. What is flame? What is atomizer? Everything we'll see now. Since you know the first part, hollow cathode lamp. Chopper is to just focus the light towards flame. Now we'll see about flame and other things. How we'll get flame in the instrument means, it is the combination of fuels and oxidants. So what are the fuels and oxidants we'll be using to get flame in atomic absorption spectroscopy, and what are the temperature range it produces. So what is the thermal flame means, it will be having high thermal energy, temperature will be very high. So what range temperature will be there, so that at that temperature your metallic atom will get atomized. Okay, for that only we need to read this fuels and oxidants. Fuels means it is a organic gases, methane, hydrogen, acetylene. These are called as fuels. Oxidant means either air or oxygen is applied. When fuel and oxidant are combined, it will give flame at the temperature range given here. For example, methane as a fuel combined with air as an oxidant, it will give the flame with the temperature range between 1700 and 1900 degrees Celsius, with the velocity of 39 to 43 centimeter per second. Likewise, when methane and oxygen are combined, it will be giving flame with the energy of 2700 to 2800 degrees Celsius, with the velocity of 370 to 390. Okay, when temperature is increases, velocity also will be increased, that you can find here. Okay, so these are all the different examples of fuel and oxidant. In lab we'll be using liquid petroleum gas as fuel, and compressor will be used for applying air. Okay, so when fuel and air is combined, it will be producing flame. Okay, And in that flame, why we require flame of higher temperature means you need to activate from neutral molecule. You want to split out an metal atom, a metal atom, in order to analyze the metal atom concentration. So how we will convert from flame of higher temperature means and Celsius, it will happen. For that only we are using this fuel and oxygen oxidant in order to get high thermal flame. And what is the nature of flame? What you get after using fuel and oxygen, after combining fuel and oxygen at that particular temperature range, how the flame produced will be having three zones. One is primary combustion zone, that is the primary zone you can find, and through the flame you can see the typical optical path, where this is the path of, that is coming from the source. Okay, this is the path coming from the source passed inside the flame. So this is optical path. Optical represents radiation path. Then interzonal region, it is interzonal region. You can see the second zonal region, and third zone is secondary combustion zone. So these are all the three zones and three regions you could find in the flame. This is structure of flame produced when fuel and air is combined. So this is part of flame, you can see. So the solution is taken, and from this is inlet for fuel, and this is inlet for air, and this will be combined to produce flame. Okay, flame will be having three zones. One is primary zone, another one is secondary zone, and interzonal region, where in the mid of the flame, radiation energy will be passed. So these are all different color of flames produced with different metal atoms. When you introduce the metallic sample solution in flame, it may give like a reddish orange color flame, or blue color, purple color flame, or blue color flame. Okay, here you can find the primary region, interzonal region, and secondary region. Like this only you will be finding flame in the atomic absorption spectrophotometer, and you will be carrying out flame photometric estimation itself in our laboratory. We have the instrument where, while analyzing, I'll show you how the flame and structure of flame is obtained when fuel and oxygen, or fuel and air is mixed, oxidants are mixed. Next is nebulizer. What is the role of nebulizer means? A nebulizer is a device that introduces a liquid sample into the atomic absorption spectrophotometer. That means this is the nebulizer. You can see a tube here that takes the sample from the container. So we'll be keeping the sample with beaker only, and it will be dipped in a capillary tube. The capillary tube serves the liquid present in the beaker, and it takes to the flame. And which part of the instrument takes the solution from the container to flame means that is nebulizer. So another part of atomic absorption spectrophotometer is nebulizer. Okay, what are the common types of nebulizers means? Pneumatic and ultrasonic nebulizer. Pneumatic name represents pressure. So at a highest pressure, when we apply the pressure, the sample solution is automatically taken as a tiny droplets to the flame. Like aerosol, it will be passed to the, or sprayed to the flame. That is the role of pneumatic nebulizer. It will happen with pressure. Where another one is ultrasonic nebulizer. Ultrasonic means the name itself, it indicates it will give the vibration energy to it, energy to the liquid solution. So vibration energy means what frequency it gives means around 20 kilohertz to several megahertz frequency is applied to the sample. So at that vibration, the liquid sample is taken from the container, and it is sprayed to the flame as an aerosol, and means droplets, liquid droplets, it will be sprayed. So these are all the types of nebulizer. So nebulizer role is what? It introduces liquid sample into flame. Instead of AS, we can give it here as flame only. It will be introducing the sample, liquid sample into the flame. So now what all the process takes place in the flame, we'll see. So now you know how the flame is produced. You have seen what is the source of light, that is holocathode lamp and EDL, electrode less discharge lamp, and EDL will not be widely used when comparing with holocathode lamp. Holocathode lamp is specific and unique for atomic absorption spectroscopic analysis. And here the flame or atomizer we are discussing, here we have seen the fuel and oxidants, when it is combined, that will be giving the flame. Okay, so how we are getting the flame in atomic absorption spectroscopy, how the flame is produced, how the flame is produced by the combination of fuel and oxidants. Okay, what are the parts of flame? It will be having three regions. One is primary combustion zone, second one is interzonal region, third one is secondary combustion zone. And in the middle of flame, radiation will be passed. Radiation energy is passed inside the high thermal energy of flame. So what will be the temperature range of flame? That will be varying from or more than 1500 degrees Celsius up to 3000 degrees Celsius. It will be varying. How the temperature is varying? Based on the fuel and oxidants used. Okay, definitely all the fuel and oxidants will combine and will give the temperature more than 1500 degrees Celsius. So that temperature range is required to convert your sample from neutral molecule to atom. Since it is atomic analysis, we need to convert the molecule into atom. Okay. So which is taking liquid sample and passing to the flame nebulizer. What is the role of nebulizer? It will introduce the liquid sample, or it will spray the liquid sample in form of liquid droplets or aerosols into the flame. So that is the role of nebulizer. There are two kinds of nebulizers, pneumatic and ultrasonic nebulizer. Pneumatic nebulizer functions based on pressure. When applying by means of pressure, applied pressure, it will be taking the liquid sample from the container, and it will be passed into the flame as a droplets or in the form of aerosol form. And like ultrasonic nebulizer will be giving vibrational energy to the sample, so whereby it will be converted to droplets and it will be sprayed to the flame. So that is the role of nebulizer. You can see here, this is the nebulizer. Okay, so sample is taken through the nebulizer, where fuel and oxidants are applied. With the pressure of oxidant and fuel itself, the sample will be taken by the nebulizer and it will be passed to the flame. Okay, and the extra sample will be drained to the to drain. You can see it will be going to the waste. Whatever sample required will be passed to the flame. So these are all types of nebulizers. You can see concentric tube nebulizer. This is first type, concentric tube nebulizer. Liquid sample is passed to the sample, where gas here represents fuel input. At the pressure of fuel itself, it will be taking the sample. So it is functioning based on pneumatic nebulizer. Based on the function of pneumatic nebulizer, since the applied pressure or pressure of gas itself allow the nebulizer to take the liquid sample from the container to flame. Then another one is cross flow nebulizer. Cross flow nebulizer. Then third one is fritted disk nebulizer. Fritted disk nebulizer. Then Babington nebulizer. These are various kinds of nebulizer. Does the same purpose and used for the same purpose. Let's see about atomization process now. Now, what are all the parts we have seen? Source of light, that is holocathode lamp, and that is passed on to the, that is radiation energy passed on to the flame. Where in the flame we have discussed how the flame was produced, what is the nature of flame, how the sample is introduced to the flame. Now the sample is introduced to the flame, and the flame is receiving radiation energy from the source. Now let's see what are the process taking place for the sample at highest temperature energy, that is highest thermal energy. That process is called automation process. That's what you have observed in the picture itself. In the first picture, atomizer, flame or atomizer. So where atomization process occurs, atomizer means atom formation occurs. It is occurring at the flame only. So now let's see what actual process occurs. Solution sample in the form of solution is sprayed, that is nebulized. Nebulizer used for the introducing or in the form of through spraying process, it will be introducing the droplets, liquid droplets of the sample to flame. So that process is called nebulization. Solution sample will be always late to the class. So sample solution will be sprayed to the flame. And that process is called nebulization through the nebulizer. So each sample particle will be surrounded with solvent particle. So from solution, it is made as a liquid droplet. So sample will be there in neutral state, but it will be covered with solvent. The next process is desolvation. So when once it is introduced in the flame, at that high thermal energy, solvents present around the sample will be removed. That is called desolvation process, where it is occurring at the highest temperature. Then that will give dry aerosol. Dry means solvent particle is removed, only the neutral molecule of sample exists. Then it goes for volatilization. Neutral molecule will be going for neutral molecule in gas state now, dried state, or in solid state now. Then after a volatilization process at the same temperature energy, what is the temperature range will be more than 1500 degrees celsius, that is obtained through the combination of fuel and oxidants. Then it will give free atoms. So neutral molecules will be splitted out and you will be getting free atoms. For example, we'll take sodium chloride solution. If you are preparing sodium chloride solution in water, sodium chloride is dissolved in water and you are taking some particular concentration of sodium chloride solution. If you are nebulizing it, if the sample is nebulized to the flame, after then at that highest temperature of fuel and oxidant in the flame, it will be dissolved. It goes for the vaporization of solvent first. Then you will get sodium chloride solid in neutral form. After when the sample is present in the same temperature for long time, it will go for volatilization and it will be converted from neutral molecule to free atoms, sodium and chloride atom. Neutral atoms will be forming from neutral molecule. Dry aerosol represents neutral molecule, sodium chloride in solid form. When it is volatilized, neutral molecule will be converted to neutral atoms. Sodium and chloride atoms, it will be splitted into atoms. So this process is called atomization. When this process takes place at highest temperature, that's why flame is used to convert a solution to free atoms. A solution will be of not atomic solution, it is molecular solution. Molecule is dissolved, sodium chloride, salt is dissolved. Or if any drug is having sodium, that will be dissolved in particular solvent and goes for the same process in order to get the free atom, metallic atom. And now once the free atoms are formed, it will be ready to absorb the radiation energy coming from the hollow cathode lamp. If sodium atom is present in the lamp, that is free atom present in the lamp, it will be absorbing characteristic radiation that is coming from the hollow cathode lamp. So what a cathode lamp is made with sodium metal, so that will be giving specific radiation wanted by the sodium metal present in the flame. Okay, that's why we are using specific cathode for each element. So no other elements will be absorbing the same wavelength, since no two elements will be having same electronic environment, even same quantum numbers. This all we have discussed, right? So definitely it will be requiring different energy of absorption, radiation energy for absorption. So that sodium metal around 580 nanometer, it will be absorbing the radiation and it goes to the excited state. So how much radiation is required to absorb by all the atoms present in flame? That will be equal to the concentration of sodium atoms present in the flame. So we can determine the concentration that is proportional to absorbance. And here you can see what are different types of atomizers. First one is one day commonly used atomizer, where other atomizers also are there with the highest temperature in order to make atom formation for atomization process. Electrothermal vaporization, electrothermal vaporization at 1200 to 3000 degrees Celsius, then inductive coupled organ plasma ICP, then direct current organ plasma, microwave induced organ plasma, then glow discharge plasma, electric arc, and electric spark. These are all the different sources for atomization process, where commonly used is flame atomizers. And these are all the elements. So in the periodic table you can find some elements are marked with pink color. These elements can be analyzed by atomic absorption spectrometric method. Okay, so but only thing, we need to use whatever element you are going to analyze, the specific hollow cathode lamp we need to purchase for analyzing the concentration of selected selected metal ion. And some elements also are analyzed. You can find all the elements mentioned with pink color could be analyzed by atomic absorption spectroscopy, including most commonly will be going with the first group and second group elements. These elements, apart from that, these all elements also are possible for analysis by atomic absorption spectroscopy. And that is about instrumentation part. So once it is absorbed, the amount of absorbed radiation will be detected by the detector will be a photo multiplier tubes. Whatever detectors and monochromators we have seen, grating monochromators will be used in order to select the radiation absorbed by sodium metal only. And then and detector will detect the radiation energy absorbed by the sample, where detectors will convert what is the role of detector? It will convert radiation energy to electrical energy. Okay, and then you will get the electrical signal, and the peak also will be appearing similar like UV visible spectrum. Whatever spectrum you get for atomic absorption will look will appear similar like UV visible spectrum. Let's see about interferences. Definitely we are using flame, so it will be having various interferences, and we are converting from neutral molecule to atom. So definitely it will be having various interferences. That is most important part in temperature techniques. That means a flame or atomic yeah, atomic absorption or atomic emission spectroscopy. These interferences are most important, and it is frequently asked question. So you can follow this tabular column for various interference types that is observed during atomic absorption spectroscopy, and what will cause to form that interference, and what is the result example of that, and correction measures, how to overcome that interference are given here. Okay, nearly you can find around 7 interferences you can find. One is ionization or vapor phase ionization interference. Instead of getting atoms, neutral atoms at the high thermal energy, the atoms will go for ionization, like how argon gas is ionized inside the hollow cathode lamp. We are giving electrical energy, and the given electrical energy, argon is getting ionized to argon positive ion, argon plus, and that positive ion is moving towards negative electrode cathode. When it strikes on the cathode, sodium metal present in the cathode is getting activated. That is, it is going to excited state to in order to emit the characteristic radiation. Right. Likewise, this what atoms, neutral atoms present in the high thermal energy, with the same temperature, it will go for ionization. So that is called ionization interference. We need to analyze neutral atoms. We don't want to analyze ions. So ions will be then interfering with the absorbance of neutral atoms. So that is the in first interference, ionization interference. And this may be called as vapor phase or cation enhancement. Atoms are ionized at the temperature of the flame or furnace, which decreases the amount of free atoms. That's what I said. No, we need to analyze free atoms absorbance, but what happens at the same temperature? It will neutral atom will go for ionization. And in order to avoid this ionization process, we can add ionization suppressor, that is nothing but buffers, to both the sample and the standard. If we add the buffers, we can minimize the ionization formation, ions formation. The next one is light scattering. Solid particles scatter the beam of light, lowering the intensity of the beam entering the monochromator. That means in the flame you could find solid residue also. You could find solid residue also. Aerosol is forming dry aerosol, that is dry residue. So what if solid particles present in the flame will do? Whatever radiation is absorbed by the sample, it will be scattered. Instead of absorption, solid particles, usually the nature of crystals, will reflect the radiation. That means it will scatter the radiation. So their loss of radiation occurs. We need to get, or we need to measure only absorbed radiation by the free atoms, not scattered radiation. Okay, so that is another interference, scattering interference, light scattering. When light scattering occurs, if solid particles are present in the flame. And this is minimized by matrix modification or background correction. By correcting, background means signal background. If we are correcting it, we can get the clear signal of only absorption. We can minimize the scattering light. Then chemical interference. If some other metals also absorbing at the same wavelength, then it will be having interference. So that is chemical interference. The example here you can see calcium and phosphate ions form calcium phosphate, which is then converted to calcium phosphate, which is highly weak. So the calcium metal will be interfering the one of answer metals. Okay, and increase the temperature also. If the absorption factor is increased, chemical or standard atomic absorption factor, adjust the temperature so that we can minimize the metal atom interference. Then use always stable with high frequency so that the interfering metal will be destroyed. Only the selective metal can be analyzed, where the chemical interference can be minimized. So we have discussed oxidation interference. Let's see about atomic line overlap. Next interference is atomic line overlap. Suppose a single profile of two elements of distance 0.00 nanometer, they will be overlapping each other. If you will be closely observing, that is the difference of 0.00 nanometer, then overlapping of atomic lines takes place. How to overcome it? Means typically it doesn't a practical situation, so there is no established correction method for this. The chemist will be having closest, very closest contact with the absorbed atomic. So, this is the process. 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 So, this
ஏ பாண்டா, ஜெட்டு, ஜானு, சக்தி, இஞ்சி, வாங்க போலாம் எல்லாரும்.
முடிஞ்சிருச்சா?
அப்படின்னு தான் நினைக்கிறேன். மேமும் இல்லையே. ஓகே, பாய்டா பாண்டா.
பாய்.
பாய் பாய் பாய்.
And thank you all. With this, I'm stopping the today's class. We'll meet in the next class.